Good morning, all of you. In today's session, we are going to start with the 10th standard chemistry and physics, where unit number 7, classification of elements, the periodic table, series number 3 is going to be discussed. In this, earlier, we started with since the inception of classification to how it is exploring, how it is evaluating, and we are discussing about Dauberny triads, Newland law of octaves have been completed, and now entered into molecular weight based classification, which was framed by Mendeleeff, right? So this is the topic going to be discussed in today's session. So apart from this, unit 1 to 6 all detailed clear explanation is available on the channel World of Competitive Chemistry. So in today's session, we are going to discuss the topic called Mendeleeff's periodic table, which purely based on molecular weight of the different elements. Now let us enter into our today's concept. Here, classification of elements in accordance with the Mendeleeff. Mendeleeff arranged all the elements known at the time in a chart in the systematic order in the increasing order of their atomic weights, right? Atomic weight is taken as the primary thing in order to place all the elements in the series in the sequential manner, ascending order of their molecular weight, their atomic weight is considered. So those are available on table 2 and modified, that means advanced periodic table of Mendeleeff. First he gave the tentative one and finally he modified into table number 2A. Let us see what is the tentative and finalized version of Mendeleeff's periodic table. So he published his periodic table classification like this. So first he assumed that hydrogen is taken in helium, boron, carbon, nitrogen, oxygen, fluorine, sodium. This is about his what publication at the time when he classified all the elements. So in accordance with their atomic masses. And this is the early periodic table where he kept some vacant sites because at the time all the elements are not known, and he thought in the futuristic way some of the elements might be present. They are not known till now, but in future they may be distinguished, they may be identified, and a certain location, certain vacant space was kept for those elements which to be identified later. So that kind of futuristic futuristic plan containing periodic table was framed by Mendeleeff, and all the elements are arranged in accordance with their increasing molecular weight, increasing atomic weight was considered. In this concept, all the elements are categorized into 1, 2, 3, 4, 5, 6, 7, and 8. So these many groups are framed here. And these horizontal locations are said to be periods. So this is about the early or tentative periodic table, which was constructed by Mendeleeff in accordance with the atomic weights. Increasing atomic weights were considered in this categorization. And further, he made all the elements in another kind of sorting where all the elements are kept and separate lanthanides and actinides also included. So at the time of Mendeleeff only, lanthanide and actinide elements are kept in a separate chamber. So yeah, I think everybody get the doubt that why lanthanide and actinides not the part of this modified Mendeleeff periodic table, and even in the modern periodic table also lanthanide and actinide elements are kept separately. What could be the reason for that one? The reason is most of the lanthanides and actinide elements are radioactive in nature. They are having the tendency to radiate the energy, emit the energy, and being all the species are highly what we can say larger in nature, nuclear size is very larger and highly unstable. That's the reason why they are used to emit the particles like alpha, beta, and gamma radiation will be emitted by these elements. That's the reason why lanthanide and actinide elements are kept in the separate distinguishable position. Right. So this is a modified version of Mendeleeff periodic table. Again, here also, after certain modifications, what he did, he kept all the elements. He arranged all the any elements in accordance with their increasing atomic weights only. But only the difference is lanthanide, actinide elements also included at this time. So this is the main foundation for the modern periodic table. So modern periodic table also having certain kind of infrastructure. That means the skeletal structure remains same, but the modifications are done based on their electronic configuration. You may say based on their atomic number as well, right? So that's the reason why it is the foundation in order to frame the modern periodic table, right? So this is the data collected from an academy. Thank you. And silent features and achievements of the Mendeleeff's periodic table. Most of the information for the classification of all the elements. At the time of Mendeleeff, so many elements were known, and so this is the kind of achievement in the classification of all the elements into various categories. So slight modification was done, and a new and modern periodic table was framed. But it is, we can say this is a kind of achievement in the classification of elements. What are the silent features? We will discuss now. Groups and subgroups. So in case of this one, you can see first A, first B, second A, second B. So here, 1, 2, 3, 4, 5, 6, all these Roman numbers are said to be main groups, and A, B kind of subcategorization is called subgroups. So here, Mendeleeff framed periodic table with the main groups as well as subgroups in that. So there are 8 vertical columns are present. If you see clearly, 1, 2, 3, 4, 5, 6, 7, 8 columns are present here. 8 columns are incorporated. Vertical means top to bottom. In the Mendeleeff periodic table, all these are considered as groups. So there are 8 groups are present in the given Mendeleeff's periodic table. They are represented by Roman numbers 1 to 8. Roman numbers are indicated for main groups. 1 to 8 Roman numbers were indicated. Elements present in the given vertical column. Always vertical column is said to be a group, right? So, similar properties. So whatever elements present in the same vertical column, you may take hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. All these elements belongs to first A group, and all these are considered as a same group elements with the similar properties or resemblance in their properties. So in this manner, so the elements which incorporated in the vertical group said to be a group, and they are possessing a similar kind of properties. Each group is divided into 2 sublevels again. One sublevel is denoted with A and the second level is denoted with B, right? So here we have 8 main groups. In 8 main groups, again subgroups are divided. A and B parameters are indicated for those subgroups. The elements within any subgroup resembles one another to a greater extent. So within the same group, if A element and B elements are present, there is a much similarity between them when compared to the external elements. When you consider gallium and scandium, being gallium is a p block and scandium is a d block element, he kept these two in a single group, both in A and B subcategories. There is a resemblance in their properties. Because of that reason, these two are kept in a same group, but subgroups are present. So categorization into subgroups are possible, right? So for example, when you consider first A group elements are regarded as alkali metals. Why all these are called alkali means when they added with water, they are possessing basic nature. So base forming elements are called alkali. Alkali means base, basic in nature, right? So here first A group elements, when you go with first A, what are first A group? Hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Among all, francium will be the radioactive element having tendency to radiate the energy, and the remaining all these first A group elements are regarded as alkali metals. When they added with water, they used to give the basic nature to the water, right? So they are having similar resemblance in their basic properties. That's the reason why all these are categorized into a single group. So they resembles other very much in their properties. So here all these elements are categorized in a vertical column called a group. That's the reason why they are possessing the similar properties, right? So this is a kind of categorization called, we can say this is a achievement given by framing groups and subgroups by Mendeleeff. And yes, So here the kind of system said to be a group, where groups are nothing but all the vertical columns are considered as a group. Group number is exactly resembles its valency electrons. At that time, valency electron term was not denoted, only purely based on molecular weight parameters they assigned. And next term is about periods. What are periods in this Mendeleeff's periodic table? Horizontal rows in the Mendeleeff periodic table are called periods. When you go to the Mendeleeff periodic table, here, when we move on from left to right hand side, so in all these horizontal columns, you can see all these are said to be periods. So here 1 to 8 vertical columns are called groups. From left to right, so these are said to be periods. How many are there? 1 to 7 periods are indicated here. So there are 7 periods in the table, which are denoted with the Arabic numbers 1 to 7. So Arabic numbers are indicated, and elements in the periods differs in their properties from one to another. So when you move on from left to right hand side, potassium to calcium, no similarity in any case, and calcium to scandium, scandium to titanium, titanium to vanadium, chromium, manganese. In this manner, when we are moving from left to right hand side, there is no similarity among the properties. Only the resemblance is possible when we are moving from top to bottom only, right? So that is the kind of system. A period comprises entire range of elements after which properties are repeated themselves. So this is a slight resemblance with the Newland active theory. So when we are moving from left to right hand side, what happens? There is a variation in the properties. And after reaching this 8th group, 9th element is going to be incorporated in the first group again, right? That's the reason why again the repetition of the properties after certain time of interval, that is the kind of instruction which is given by Newland theory of octave. So that also agreed by this Mendeleeff periodic table, right? So here elements in a period differs in their properties from one another. A period comprises of entire range of elements where the properties repeated themselves. Repetition of properties are possible after certain periodic interval, right? So these are said to be periods. For horizontal are called periods, vertical columns are called groups. Right, so here when we are moving from left to right hand side, these are said to be periods. When we enter into new period, new shell will be started. That means new principal quantum number will be added. Okay, here hydrogen, for example, you may have 1s1. When you move on to lithium, being it is a second group element, 2s1. That means a quantum number got increased. From lithium to sodium, what happens? Lithium to sodium, it will become 3s1. That means one more principal quantum number got added. That is nothing but new period will be started with a new shell. So this is a kind of system which observed in the periods left to right hand side called the horizontal columns. Now, another achievement are silent feature given by the Mendeleeff, predicting the properties of missing elements. This is the futuristic vision of this Mendeleeff periodic table. So here at the time, whatever elements are known, he arranged all the elements and even kept some empty gaps, empty vacant sites for future identification of the elements. He gave the scope to future researchers, and there is a structural and properties resemblance, and they are suitable in their vacant sites. He thought like that. So these missing sites, based on the arrangement of elements in the table, he predicted some elements were missing, left blank spaces, appropriate places in the table. You can clearly observe what are the vacant sites available in the Mendeleeff's periodic table. So this is for the future identification of elements. Here, Mendeleeff believed that some new elements would be discovered definitely. In the future, there are so many elements are going to be incorporated into the system. He predicted the properties of those new elements. He assumed without knowing what element is going to be invented, but according to the periodicity, he assumed the properties. He mentioned the properties of those unknown elements also. Right, that is the kind of advanced thinking. We can say it is the kind of advanced thinking. that purely depending upon the table. His predicted properties were almost resemble with the elements which are discovered later. In the future days, whatever elements discovered, that are possessing the properties what Mendeleeff expected. So here, some of the elements categorized in this table. Eka aluminium he predicted. So he thought that Eka aluminium is 68, gallium 69. So there is a resemblance. So he felt, so because Eka nothing but one more extra, that means addition of one later to that one. After aluminium, we got empty space, right? That's the reason why it is mentioned as a Eka aluminium. He assumed its atomic weight is given as 68. After the invention of element called gallium, its atomic weight is given as 69. There is a maximum resemblance in the atomic mass, even though he don't know what element is going to be invented. So that kind of advanced thinking he kept in this periodic table classification. And one more element called Eka silicon. He assumed its atomic weight will be 72. So after the invention, researchers found germanium as the element which is suitable with this Eka silicon. Eka silicon is identified as a germanium whose atomic weight is given as 72.3, almost equal. What he assumed, what invented later, both are exactly coinciding with each other. And the density is also in the same region what is expected, what is calculated, right? And melting point values, boiling point values for those maximum number of valency electrons present in their outer level, what he expected and what invented later, all are exactly resembling. That indicates his advanced thinking level. In these vacant sites, elements are going to be invented and they may possess certain properties which are mentioned in this table. He assumed their atomic weights, density values, melting point, boiling point values, number of valence electrons, and even oxidation properties of all those elements. After the invention, they are having equal or resembling properties what he expected, right? So what elements we measured here? Eka aluminium is identified as a gallium. Eka silicon is identified as a germanium. So this table was between the assumption and the actual invention. So that kind of tabular form is represented here. And one more achievement, in continuation to this one, here he mentioned as a Eka aluminium, Eka silicon, right? So here he named those elements tentatively by adding prefix Eka. This Eka is the word which is given from the Sanskrit. So Eka denotes what? In Sanskrit, Eka denotes one, right? So the name of the element immediately above each empty space. So here, for example, aluminium is 11 and the element going to be invented will be 12. Means one more extra that is given by Eka aluminium, that word taken from the Sanskrit whose meaning will be 1. The predicted properties of elements, namely Eka boron, Eka aluminium, Eka silicon, were almost same as the scandium, gallium and germanium respectively. That is nothing but Eka boron is invented as a scandium, and Eka aluminium is a gallium, Eka silicon will be germanium. So in this way here he assumed one more extra will be there, and after the invention they're also having equal properties, and the word Eka is taken from the Sanskrit. Eka means one, ek, right? And these are the elements what he kept the gaps and what invented later. Mendeleeff's assumed names are Eka aluminium, further invented as a gallium, Eka boron invented as a scandium, Eka silicon as a germanium, Eka manganese as a technetium, trimanganese, mortri, rhenium, and dwitellurium, polonium, dicesium called a francium, Eka tantalum. Eka tantalum is a protactinium. So these are the modern names which are provided after the invention. These are the names which assumed they may be going to be invented in future. So that kind of Mendeleeff names and modern names are given in this tablet form. Now, Mendeleeff thinking, just now we got the comparison between Eka aluminium with gallium and Eka silicon with germanium. Same again repeated here. Their density, atomic weight values, formula of oxides and formula of fluorides also mentioned. what he assumed and almost similar to the predicted property. And one more interesting thing in the Mendeleeff periodic table, do you know that Mendeleeff said about the melting point of aluminium? Aluminium is nothing but after aluminium, what is going to be given? That is aluminium is given as a gallium, right? So that gallium, what he felt is its a melting point value. So its a melting point value will be when we are taking that gallium into the hand, that involved in melting with our hand temperature only, it will melt. He felt like that, even though that element is not known to us, but he assumed, he thought that, so by taking the gallium element into hand, that will melt, our hand temperature will melt that one. But interestingly, after the invention, the element gallium has the melting point value 30.2. Our body temperature will be 37 in general, right? So that's the reason why when gallium, being it is a solid material, always it will be in a solid state. But when taken into the hand, that will melt in such a manner what he felt. So that is the futuristic vision of a Mendeleeff. Even though the things are unknown, he assumed, but they came to reality after the invention. So this is also another kind of assumption came into reality. And next is about correction of atomic weights. So the initially he gave a tentative table for all the elements classification. Later on, he made some modifications in the modern, and his own modification or advanced table was given. So he made some corrections to the atomic weights. So already established atomic weights made into corrected. So they got modified, then accurate molecular atomic weight values are given in the new or modern periodic table of himself, right? The placement of elements in the Mendeleeff periodic table helped in correcting the atomic masses of some elements like beryllium. So already established and newly corrected one. So based on his periodic table only, beryllium, indium, and also gold, whose atomic weight values which already established, and they made corrected into accurate values. This is also, we can say, the achievement given by this Mendeleeff's periodic table. What already established for beryllium, indium, and gold, so they got modified and made into a correct integer value. For example, at the time of Mendeleeff, beryllium was given as atomic weight 13.5. Atomic weight is given as 13.5. Atomic weight is calculated by taking the formula equivalent weight into valency. In general periodic table, here atomic number and atomic mass is indicated like this. Atomic weight is nothing but atomic mass only. Always a superscript denotes what atomic number, and the subscript denotes atomic mass of that particular element. In order to calculate the atomic weight, Mendeleeff gave the formula that equivalent weight that is multiplied with the valency, right? So here another practice problem was given to you, which based on this atomic weight calculation, atomic weight of the element is taken as 30 and its equivalent weight is 10. Then what could be the valency of the element? Based on this formula, so we got one problem for practice. So I collected this problem from topper. Thank you. So here atomic weight and equivalent weight both are given, and the thing we need to calculate will be valency. Here atomic weight and equivalent weight, these two parameters are known, only the thing is valency to be predicted, right? So for that purpose, valency is equal to atomic weight by equivalent weight. Atomic weight is given as 30, by equivalent weight is given by 10. The 0, 0 get cancelled, then it will become, valency will become 3. That means it able to form a 3 bonds. So element is unknown to us. Based on atomic weight and equivalent weight, it is possible to calculate its valency. Valency denotes a number of electrons it is going to be lost. Otherwise, you can say number of bonds it able to form. Both are similar only, right? So that is called a valency, and that is calculated by the formula which is provided by this Mendeleeff, correction of atomic weights. So this is also the achievement we can say. And the equivalent weight of beryllium was found to be 4.5. Equivalent weight is given as 4.5 and the valency will be 3. 4.5 when multiplied with 3, it will be 13.5. So here 13.5. So beryllium atomic weight is given as a 13.5 in accordance with his empirical formula, which is given as atomic weight is equal to equivalent weight into valency. 4.5 into 3, 13.5, that exactly matching. With this atomic weight, he had placed a wrong group in the table. He said that valency should be only 2. Then its atomic weight 4.5 into 2 is equal to 9. So atomic mass will become 9. So here the element will be beryllium, right? Already established valency is 3. So then 13.5 was given. But he assumed that its valency will be 2 only rather than 3. So this is already established value. He made a correction like that. 4.5 can be multiplied with 2 rather than 3 so that it will become 9 only. So beryllium is 9, would be fit in the second group. Let us move on to his periodic table. Yes, where beryllium was given, this beryllium 9.01 is the exact atomic weight. Already established value is 13.5, but based on his correction, he converted, he concised, he reduced the value of atomic weight from 13.5 to 9.0. So in this manner, you can arrange this in the ascending order of atomic weights, and it will be in the suitable position. Even in the modern periodic table, in the second group only beryllium was kept. So his assumption is correct with respect to this correction in the atomic weights. That is also, we can say, achievement done by this Mendeleeff periodic table. So beryllium valency will be 2. That means it able to form a 2 bonds. Beryllium being it is a linear molecule. When you take beryllium chloride, 2 chlorides will be on the same plane, right? So that is a 2 valency bivalent system. So if atomic weight of beryllium is 9, it would be fit in the second group only. Even in the modern periodic table, you can find this beryllium in the second group itself. That is the correct position. And its properties practically similar to magnesium and calcium of the second group elements. So because being it is a kind of alkaline earth metal, beryllium, magnesium, calcium, all these grouped in a single one, that is a second group element only. He also helped in the calculation of correct atomic weights of indium and also gold. Here we mentioned indium. Indium, its atomic number is 49, being it is the element of third group. So here 49 is the atomic number. Its valency electronic configuration is mentioned like this. A krypton is a noble gas configuration which is near to this indium, and 4d10 configuration will be there, 5s2, 5p1, so that it is a kind of p block element. And you can say post transition metal. What is meant by post transition metal? Immediately after transition metal, this element will be placed. That's why you can say it is a post transition metal. Pre transition metal in the sense it is present before transition metals. Post transition metals nothing but after transition metal element, this element was placed, and whose atomic mass is 114.8, which is calculated based on his formula. Atomic weight is equal to equivalent weight into valency, right? So this is the corrected atomic mass, which is agreed by even modern periodic table also. And one more element is a gold. So gold is indicated with Rm. Au is the scientific name of this one, IUPAC name of this one, right? So here, in case of gold, atomic number will be 79, whose atomic mass will be 196.96. Again, it is calculated based on the formula which is provided by this Mendeleeff theory, right? So these are also corrected. These 3 elements. Which elements? So one is a beryllium, second is indium, third is aurum. These 3 element atomic masses, whatever established earlier, got corrected based on his theory, which accepted even by this modern periodic table also, right? So this is another achievement we can say. And anomalous series. So one more ambiguity he observed. Some anomalous series of elements like tellurium and iodine was observed in the table. So we can say this is a kind of ambiguity or limitation, obstacle. So how it will be? Actually, what he said, all the elements arranged in the periodic table, as in the case of ascending order of atomic masses, increasing level of their atomic masses will be observed. But when you observe this tellurium and iodine, tellurium atomic mass will be 127, iodine will be 126. What should be the order? Iodine, iodine, and the next preceding element will be tellurium, right? But he arranged in a reverse manner. What he gave the statement that is not applicable to this one, this is said to be anomalous series. And the anomalous series contained elements with more atomic weights, like a tellurium with a 127, placed before the element with the less atomic mass of iodine with a 126. Actually, according to his statement, 126 next 127 should come. Order should be reversed. But he placed a tellurium followed by iodine. You can say this is the anomalous series. Mendeleeff accepted minor inversions in the order of increasing atomic weights, as this inversion resulted in the elements being placed in the correct groups. So he accepted, even though all the elements are arranged in the increasing order, but some limitations are there, some exceptional cases are there where I placed all the elements not according to that increasing the atomic weight. Some exceptional conditions also present, just like tellurium and iodine, right? So this is a kind of obstacle we can say. And in Mendeleeff periodic table, it was extraordinary thinking of Mendeleeff that made a chemist to accept the periodic table and recognize Mendeleeff more than anyone else in the originator of the periodic law. So here, most of the chemists strongly agreed he's a kind of vision, he's a kind of arrangement of all the elements what are known at the time, and their properties are mostly satisfied. So what he gave the explanation, that is in the satisfactory manner by the chemist who are doing the research on that. That's the reason why it is the widely accepted kind of theory or classification for the categorization of all the elements at the time. At the time of Mendeleeff, he introduced his periodic table. Even electrons were not discovered. So at the time, he only assumed based on atomic weight. At the time, electron invention is also not done. This is also carried in the 18th century. At the time, the term electron is not known to anybody, right? Even then, periodic table was able to provide the scientific base for the study of chemistry of the elements. Even electrons are not known. Actually, pure chemistry mainly maximum depends upon the kind of electrons, nature of electrons. Based on that nature only, type of bond formation. Entire chemistry purely based on the electrons only. But Mendeleeff theory, when he gave the entire classification, the term electron is not at all known. But still, most of the scientific assumption made by this Mendeleeff were acceptable. They're also correlated after the invention of electrons also. In his honor, because of his maximum contribution towards the development of this classification, in his honor, the 101th element in the periodic table was named on his honor, that is called a Mendeleevium. Mendeleevium is the element of 101, that is of 5F13, being it is a F block element. It is the synthetically manufactured, but in order to give the honor to him, the name is what contributed to him. So a block element, you can say actinide element, it will be 101, and the atomic mass is given as 258.1. 5F13 and 7s2 is the electronic configuration of this Mendeleeff, being a purely modern periodic table based on the electronic configuration. Even he don't know what is the electron and how the arrangement is possible based on electrons, but most of the properties are satisfied even after the invention of modern periodic table also. That's the reason why he got honor by contributing the name to one element. And we have certain limitations with this Mendeleeff's periodic table, anomalous pair of elements. So that is a kind of obstacle we can say. Just now we discussed the tellurium placed earlier when compared to iodine, being tellurium is a higher atomic weight and iodine will be the lesser atomic weight. This is the kind of obstacle, but some minute, that means we can say this is a kind of exceptional condition. but most of the elements, whatever placed by this Mendeleeff, are still acceptable in the modern periodic table as well, right? So this is a kind of limitation you can observe in the Mendeleeff periodic table. And some other limitations which are faced by Mendeleeff periodic table. Because of these limitations only, we entered into a new theory. Always there is a how water is flowing by a river. In the similar manner, science is going to be explored. Even in the future also, we will get so many modifications in this new periodic table also. That's the reason why always there is evaluation, right? So here certain limitations are present in the Mendeleeff periodic table. Dissimilar elements placed together. So here, actually in a single group, what he gave the statement. So the statement is whatever elements placed in the group, all are having equal properties or resemblance in their properties. But there is contradictory condition we observed for few elements. Elements with the dissimilar properties were placed in the same group or subgroup. Right. So here the elements like lithium, sodium, potassium, first A group have a little resemblance with the coinage metals like copper, silver, or so here lithium, sodium, potassium are regarded as alkali metals. Copper, silver, are called coinage metals. Coinage metals are nothing but the coins. Those coins are made up of these metals only, copper, silver, aurum. So these groups are placed together. These lithium, sodium, potassium are regarded as a first A. Copper, silver are considered as a first B. But so when they kept in the what he said, so here subgroups when present there is a similarity, but when you consider actually there is no resemblance in any kind of properties between them, because lithium, sodium, potassium are soft metals. S block elements are said to be soft metals. Copper, silver, iron are coinage metals. They are very strong, very hard metals, we can say, right? So here there is no resemblance, and these are S block elements, these are D block elements. No resemblance will be there. This is a contradictory statement which is given by this Mendeleeff. And the chlorine is grouped in 5th, 6th, 7th. 7th A, manganese in 5th, 6th, 7th B. So chlorine being it is a non-metal, manganese it is the D block metallic element, transition metal it is. But 7th A, 7th B, how can we assume both are similar? Because chlorine is a gas, manganese is a solid. Chlorine is a non-metal, manganese is a metal. Chlorine is a P block element, manganese is a D block element. In all kind of properties, in all possible directions, there is no relation between these two, but still they are grouped into a same one. 7th group, A and B subcategories will be there. This is also, we can say, a limitation given by Mendeleeff periodic table. But chlorine is a non-metal, manganese is a metal, so properties resemblance will not be possible for these two. So this is also a limitation given, right? So this is a kind of system which is provided by Mendeleeff. Main groups are present and subgroups also present here, and these are said to be periods. Here some think and discuss kind of questions are given to us. Why Mendeleeff had to leave certain blank spaces in the periodic table? What is your explanation for this? Why he kept some empty spaces in the periodic table? Mendeleeff left some gaps in his periodic table because all the elements are not discovered yet. In future, there is a invention of new elements, so that they should placed in the proper places in accordance with their atomic mass and also with their property resemblance in the different groups. By looking at the chemical properties and physical properties of the elements next to the gap, he could also predict the properties of these undiscovered elements. The elements germanium was discovered later, but its properties are predetermined. Properties are known, element determined later. That is the kind of system given by this Mendeleeff. And one more question we got: what is your understanding about EA2O3, ESO2? So this is a think and discuss question in your academic textbook. I got this answer from Brainly. Thank you for this. EA denotes what? Eka, aluminium oxide. A denotes aluminium, E denotes Eka. And S denotes Eka. Sorry, E denotes Eka, S denotes silicon, right? So Eka silicon oxide, these two were given to us. What is your understanding about Eka aluminium oxide and Eka silicon oxide? E2O3 oxide of eka aluminium predicted by Mendeleeff. EsO2 is the oxide of eka silicon predicted by Mendeleeff. In 1875, eka aluminium was found to be gallium oxide. So what he mentioned, so E2O3, same kind of valency is also applicable to newly invented element gallium, Ga2O3. Ea now replaced with Ga because Ea is eka aluminium. What name given by Mendeleeff? Newly invented name will be gallium. Both are having same resemblance in the oxide formation. What he assumed, eka silicon is given as EsO2. Now it is invented as germanium, but the valency is exactly same, GeO2. So that means O2, two oxygens are required. So valency will not be varied. What he assumed and what formed actually will be exactly coinciding with each other. So that kind of understanding I got from this. Ea2O3 is now replaced with Ga2O3 because eka aluminium is a gallium. Then Es2O2 now replaced with GeO2 because eka silicon will be germanium oxide. So this is a kind of observation. Now, all alkali metals are solids, but hydrogen is a gas. This is a kind of exceptional condition, you can say. Again, it is a kind of think and discussion type. So exceptional condition in the entire periodic table, hydrogen is unique. Why we can say? Being it is a atomic number 1, atomic mass is also 1, that is a unique one, we can say. And there is a contradictory placement of hydrogen in the S block or P block. So two resemblance will be there. How can we explain its position in the periodic table? All alkali metals are solids, but hydrogen is a gas with a diatomic molecule. Do you justify the inclusion of hydrogen in the first group with alkali metals? How can we justify? Hydrogen is not a metal, but all the first group elements are considered as metals only. Except hydrogen, you can go with lithium, you can go with sodium, potassium, rubidium, all these are the metals only, but hydrogen placed along with them. Even in the modern periodic table also, hydrogen placed along with these S block elements only. Then how can we justify the statement? Moreover, hydrogen is able to form a diatomic species H2. But when you take sodium, it will not form that Na2, or lithium will not form Li2. So that kind of resemblance is also not there. So then on what basis you can place hydrogen with these S block elements? We have to give the justification for this exceptional condition. Let us discuss. I collected this answer from Brainly. Thank you for this. The similarity of hydrogen with alkali metals with NS1, right? So hydrogen being it is 1s1 electronic configuration, lithium with the 2s1, sodium with 3s1, potassium with 4s1. In the same manner, outer electronic configuration will be similar for all these S block first group elements. And hydrogen able to lose one electron and gives a place one oxidation state. Even lithium able to lose electron, Li plus, sodium Na plus, potassium K plus. In that manner, be able to give place one as a common oxidation state. And hydrogen, because of its smaller size, high electron negativity, it is a non-metal and high ionization potential will be there. That's the reason why it able to form a covalent compound rather than ionic bond formation. All the first group elements are able to participate in the ionic bond formation, but exceptionally, hydrogen participate in the covalent bond formation. That is because being it is a smaller one, high electron negativity will be there. That's the reason why it able to share the electron with another hydrogen. Due to the weak van der Waals forces of attractions of gas it used to exist in the form of gaseous state. And alkali metals are strongly formed by the intermetallic three-dimensional bond formation. That's the reason why lithium, sodium, potassium all exist in the solid state only, but exceptionally hydrogen, being all the bonds are weak van der Waals forces, that's the reason why it exists in the gaseous state. Hydrogen in general, we can say some extent resemblance is there. That is one thing is its electronic configuration, because the modern periodic table purely based on the foundation of its outer electronic configuration. Similar outer electronic configuration, similar group it will be. So hydrogen also having similar electronic configuration like lithium, sodium, potassium. That's the reason why it kept in that. Then one more thing I would like to discuss, that is hydrogen also having resemblance with a p block element. How can we say? By gaining one more electron, what happens? It used to attain the noble gas configuration helium. So if we give one more electron to hydrogen, what it will form? It will form H minus. When H minus is generated, H minus having two electrons. Two electrons are the noble gas, stable configuration, helium. So that is the tendency given for halogens. That's the reason why hydrogen also found the position in the halogen family. So there is a possibility, because if similar resemblance is there, if electron gaining tendency is there, so that is the property of halogen elements. So because of that nature, you may place this hydrogen even in the p block elements also. So this is the exceptional condition which is not applicable to any other element other than hydrogen. Hydrogen may placed in S block, may placed in P block, because S block resemblances NS1 electronic configuration. P block resemblances electron gaining tendency to attain the noble gas configuration. Fluorine when take electron, what happens? Fluorine now converted into neon. That means a stable electronic configuration, noble gas configuration. In the similar manner, hydrogen also by gaining one electron, it will attain the noble gas. So here there is an exceptional condition which applicable to this hydrogen, right? So by this we completed Mendeleeff periodic table in the series number 3. And in the next session, we are going to discuss about the modern periodic table, which are purely based on the atomic number, and you can say electronic configuration of the various elements. And hope this session will be helpful for your preparation. Thank you very much for your consistent listening. Thank you, one and all.